In this video we're going to be introduced to reduction-oxidation reactions and a related concept of oxidation numbers. So first, let's take a look at a video. This is a video where we have magnesium metal and it's being heated up and it's going to react with oxygen in the air to form magnesium oxide. So the magnesium burns really effectively and gives off this characteristic, extremely bright flame. So this reaction between magnesium and oxygen is an example of a reduction-oxidation reaction. And very often we shorten that. Rather than saying reduction-oxidation, we just say redox. Now, redox reactions are an important class of reactions that's characterized by the transfer of electrons. And it's not always true, but it is not uncommon for redox reactions to be extremely energetic, like this reaction between magnesium and oxygen. And so, to see how the electrons are being transferred, what we want to do is we want to consider what are the charges on all of the chemical species, on all of the atoms, really, in all of the chemical species in my equation. Right, so here we have magnesium solid, right? And so this is elemental magnesium. Magnesium doesn't have to have a +2 charge. It only has a +2 charge when it's an ion. If I have elemental magnesium, like this magnesium ribbon started out as, it has a charge of 0. Similarly, O2, elemental oxygen, does not have a charge. Now, when I form the ionic compound magnesium oxide, now they do have charges. So the magnesium is +2 and the oxygen is -2. And so now I think you can see, right, redox reactions involve the transfer of electrons. While magnesium is going from a charge of 0 to a charge of +2, each of the magnesium atoms is losing 2 electrons, and the oxygen is going from 0 to -2, meaning each of the oxygen atoms is gaining 2 electrons. So the electrons are being transferred from the magnesium to the oxygen. So that's what makes this a redox reaction. Now, in terms of terminology, so we have these terms reduction and oxidation. So one of the elements in a redox reaction is always reduced and another element is always oxidized. It turns out that in this case it's the magnesium that's oxidized. The element that gives up, or the atom that gives up the electrons, is said to be oxidized, and the atom that gains the electrons is said to be reduced. And so sometimes it can be hard or easy to get these terms backwards, right? So the way I always remember it is the charge on oxygen went from 0 to -2, so I would say that charge was reduced. So that's how I remember that the one that gains electrons, right, its charge becomes more negative, that's the one that's reduced. And the ones that become more positive, the ones that lose electrons, those are oxidized. So in the last example, it was fairly easy to see where the electrons were going, because I went from things that didn't have charges to things that did have charges. But particularly when I have reactions that only involve covalent compounds, nothing has charges, and so it can be difficult to figure out whether electrons are being transferred, and if so, what are they being transferred from and to. So the way we have to keep track of the electrons is a bookkeeping technique called oxidation numbers. And so oxidation numbers, sometimes also called oxidation states, are a way for us to keep track of the electrons. Now, they're going to look a lot like charges, but they're not necessarily charges. In the case of monatomic ions, they are exactly the same thing. In the last example, in the product, the magnesium oxide had an oxidation state of +2, and it had a charge of +2. And oxygen had an oxidation state of -2, and it had a charge of -2. But for covalent compounds or polyatomic ions, they're just a bookkeeping technique. They're not actually the charges, but they do allow us to determine where the electrons are going. Now, the oxidation number, or the oxidation state of an atom, is equal to charge that atom would have if all of these shared electrons were completely held by the one that attracts them the more strongly. Right? So this goes back to water. We said water is polar because the electrons are more attracted to the oxygen. And so if oxygen got all of the shared electrons completely, then it would have a -2 charge, and each of the hydrogen would be a +1. Now we know that's not true. We know that they really only have positive charges. This is just how it works in the case of oxidation numbers or oxidation states. Now the good news is we have some fairly simple rules for determining the oxidation number of an element in a compound. They may seem a little bit complicated at first. What you may want to do is pause the video, write them down, and then we'll use these in some examples, and I think they'll make a lot more sense. Now, a lot of these rules are things that we already know about being able to predict the charges of things when they form ionic compounds. For determining the oxidation numbers, the oxidation states, even though they're not necessarily charges in the case of covalent compounds, the rules are similar. So the first rule is that if I add up all the oxidation numbers of the atoms in a neutral molecule, the oxidation numbers have to add up to be 0. And if I have a polyatomic ion, like if I have nitrate, when I add up the oxidation numbers of the nitrogen and the 3 oxygens, they have to add up to be -1. Alright, free elements have oxidation states of 0, and we saw that in one of the very first slides, right? The free magnesium, elemental magnesium, had a charge and an oxidation state of 0, and the oxygen had an oxidation state of 0. And monatomic ions, the oxidation state is the charge. So when I saw magnesium oxide, right, that's composed of 2 monatomic ions. The magnesium has a charge of +2 and it has an oxidation state of +2. And the oxygen has a charge of -2 and it has an oxidation state of -2. Now the rest of these rules really come in a hierarchy. And as we're going to see, elements don't always get to have the oxidation states that they would normally like. And the higher they are in this list, the more likely they are to get the oxidation state that they want. So the cations that have predictable charges, they always get the charges they want, or they always get the oxidation states that they want. So alkaline metals, they're always going to have an oxidation state of +1, alkaline earth metals +2, and aluminum, zinc, and silver. Right? So that's really nothing new. The only new thing is they get to have the oxidation states that they want over everything else. Then fluorine comes next. It will always be -1 unless there's some weird combination of how it's paired with these up here where it's not, and I can't even think of a case. So pretty much fluorine always gets to be -1. Hydrogen always likes to be +1 unless one of the things up here takes precedence. So for example, if I made sodium hydride, so sodium is an alkaline metal, so it gets the charge and oxidation state that it wants. So the sodium is +1. Well, in order for this whole thing to be neutral, the hydrogen has to adopt an oxidation state of -1. So then when I do the +1 and the -1, I get 0. Right? If I have water, hydrogen is higher in the list than oxygen, so hydrogen gets to have an oxidation state of +1 in water. Now, if both of the hydrogens are +1, it turns out the oxygen also gets to have the oxidation state that it wants of -2, but hydrogen would get the priority there. So oxygen comes next in terms of priority. We know oxygen likes to be -2. As long as its pairing with one of the things up here doesn't mess it up, oxygen will be -2. The halogens other than fluorine like to be -1 unless something up here has higher precedence. Sulfur is in the same column as oxygen, so we know that it would like to be -2. Nitrogen likes to be -3. And then the other elements, we don't necessarily know what their charges would be, but we'd be able to predict them based on their combination with these other elements that have higher priority. Alright, so this may seem a little confusing, but let's take a look at some examples and I think it'll help clear things up. Alright, so I want to assign oxidation states to every atom in each of the following species. So when I look at the first one, I have chromium and oxygen. This is an ionic compound, so I really just have 2 monatomic ions. So in the case of 2 monatomic ions, when they ask me to assign the oxidation states, they're just asking me to assign the charges. And so I know how to do that from when we were naming things. Right, I have 1 chromium and 3 oxygens, and because this thing is neutral, their charges and their oxidation states have to add up to be 0. So I would do a little formula, right? I have 1 cation plus 3 oxygens that are negative 2. That has to add up to be 0. So the cation minus 6 is equal to 0. So the cation is plus 6. So the chromium has a 6 plus oxidation state. The oxygen has a 2 minus oxidation state. Now when I go to the chlorate ion, now I have 2 nonmetals that are combined to form this polyatomic ion. And the oxidation states have to add up to be the overall charge of the ion. They have to add up to be negative 1. So the chlorine and the oxygens don't get to have the oxidation states that they would normally want. Right? Oxygen likes to be negative 2, chlorine likes to be negative 1. If they all got what they wanted, right, I have 3 negative 2s plus a negative 1, that would be negative 7, and that's not the case. So the list that we had on the previous slide, if you wrote those down, oxygen is higher than chlorine. So oxygen gets the oxidation state that it wants. Chlorine has to adopt whatever oxidation state it needs to for the whole ion to be negative 1. But I'll figure that oxidation state out just like I did here for determining the charge. Right? So I would say, okay, I've got 1 chlorine. That's the oxidation state I'm trying to find, because oxygen gets what it wants. Oxygen, there's 3 of them. Because oxygen has higher priority, it gets to be negative 2. And then the oxidation states have to add up to the overall charge. So I have a chlorine minus 6 is equal to negative 1. So then add 6 to both sides. So the oxidation state of chlorine in a perchlorate ion is in fact plus 5. So the oxidation states are plus 5 for the chlorine, and then oxygen got to be the negative 2 that it normally wants to be. Alright, so let's look at some more examples. So now I have sodium sulfate. So I have an ionic compound, but it's composed of a monatomic ion and a polyatomic ion. When we're doing the polyatomic ions, I think it helps to just figure them out by themselves. So I have this monatomic ion sodium. Well, I know the charge that sodium is going to have. It's going to be plus 1. So my oxidation state, sodium plus 1. And then we're just going to treat the sulfate by itself. Right? It doesn't matter what sulfate's paired with. It's always SO4 2 minus. So the sulfur and the 4 oxygens have to add up to be negative 2. And again, if you go back to the list of priorities, oxygen is higher in the list than sulfur. So oxygen gets its negative 2, and then sulfur has to be whatever it needs to be for the ion to have an overall charge of negative 2. So I have 1 sulfur, I have 4 oxygens, each one is negative 2, and then they have to add up to be the overall charge, so they have to add up to be negative 2, and so S minus 8 is negative 2, so I'll add 8 to both sides, so sulfur is plus 6. So the oxidation states in sodium sulfate, sodium is plus 1, oxygen minus 2, sulfur plus 6. If we do another example, now I have copper nitrate, right? And copper is a monatomic ion, and I don't know what the charge on copper is going to be all the time, but because it's a monatomic ion, the oxidation state is the same thing as the charge. So I just want to know what is the charge on copper in this compound. And so to do that, I can use the polyatomic ion, right? I know nitrate is negative 1, right? And I have 2 of them. So in order for this compound to be neutral, the copper needs to be plus 2, right? If we were to name that, it would obviously be copper 2 nitrate. So my oxidation states, copper is plus 2. And now when I focus on the elements in the polyatomic ion, I have the nitrogen and the oxygen. Again, nitrogen is higher in the priority list. Oxygen is higher in the priority list than nitrogen. So the oxygen gets the negative 2 that it wants. And nitrogen has to be whatever it has to be for the ion to be negative 1 overall. So I've got 1 nitrogen, 3 oxygens that are negative 2. It has to add up to be negative 1, so N minus 6. Add 6 to both sides. So my oxidation states in copper 2 nitrate, the copper is plus 2, oxygen is minus 2, and the nitrogen is plus 5. I know I'm going to keep going, but I think the easiest way to do these is to do more examples. So now I have just a purely covalent compound. I have carbon and oxygen. They have to add up to be 0. So again, when I go to the list, carbon is in the very bottom. It's not one of the listed elements, so it's just going to have to be whatever it has to be for oxygen to get its -2. So oxygen is going to be -2. I have 1 carbon, 2 oxygens at -2. Right now it has to add up to be 0. So C minus 4 is 0. So in carbon dioxide, the carbon's oxidation state plus 4. Here I have a monatomic ion, and so manganese is not one of the elements who I always know what its charge is going to be, but that's fine. I would be just determining the charges like I would for any ionic compound. I know oxygen is going to have a -2 charge when it's an ionic compound, so 2 manganese, I have 7 -2 oxygens. They have to add up to be 0. So 2 manganese minus 14 is 0. So add 14 to both sides. 2 manganese is 14. Divide by 2. Each manganese is plus 7. So this is manganese 7 oxide. So those would be my oxidation states. All right, I wanted to do one last example. We saw a lot of oxygen, right? And oxygen almost always gets the priority that it wants. But if you look, or it gets priority almost over everything, and so it gets the oxidation state that it wants, right? But if you go back to the list, fluorine outranks oxygen. And so fluorine wants to be -1. Because it has higher priority, it gets that -1. And now this is a case where oxygen has to adopt whatever oxidation state it needs to give the overall compound a charge of 0. So now, and I'm not going to write O for oxygen because that's going to get confused with a 0. So I'll say oxygen, I've got 2 fluorines at -1. It has to have to be 0. So oxygen minus 2 is 0. So in oxygen difluoride, oxygen actually has a +2 oxidation state.